In this lesson, we'll learn how derivatives can be used to classify local extrema. Recall that the derivative is related to the slope of a function. If f prime is less than 0 for all x in an open interval, then the function is decreasing. And if f prime is equal to 0 for all x in the open interval, then the function is constant. And if f prime is greater than 0 for all x in the open interval, then the function is increasing. So how can we find these intervals where the function is increasing, decreasing, or is constant? Well, the way to do that is to find the critical numbers and use them to determine test intervals. Then we determine the sign of the derivative in each of the intervals. Let's look at an example. Find the open intervals on which this function is increasing or decreasing. First, differentiate and set f prime equal to 0. And after we factor, we get critical numbers at x equals 0 and 1. Because there aren't any points for which f prime doesn't exist, we can conclude that these are the only critical numbers. Now let's set up our test intervals. To the left of 0, let's pick negative 1. F prime of negative 1 is 3 plus 3 equals 6. Since f prime is positive, that means the function is increasing on this interval. Now let's test the interval between our two critical numbers, between 0 and 1. Let's pick x equals 1/2. F prime of 1/2 is 3/4 minus 3/2 equals negative 3/4. Since f prime is less than 0, the function is decreasing on that interval. Finally, let's check something to the right of x equals 1. Let's pick x equals 2. F prime of 2 is 12 minus 6 is 6. Since f prime is greater than 0, the function is increasing on that interval. Here's what our function looks like. Now, what do you notice about the derivative of this function at its local maximum and minimum points? There's a local maximum at x equals 0 and a local minimum at x equals 1. Near the local maximum, the derivative is positive on the left and negative on the right. Near the local minimum, the derivative is negative on the left and positive on the right. This takes us to the first derivative test, which we'll use to locate local extrema. Once you find the critical numbers, let's call those c. If f prime changes from negative to positive at c, then the function has a local minimum at c, f of c. And if f prime changes from positive to negative at c, then the function has a local maximum at the point c, f of c. And if f prime of x is positive on both sides of c, or negative on both sides of c, then f of c is neither a local minimum nor maximum. Let's do an example. Find the local extrema of this function. The domain of this function is all real numbers. You can take the cube root of any real number, and since power functions are continuous on their domains, this function is continuous everywhere. Alright, step 1. Let's take the derivative. Using the chain rule, take the derivative of the outside function times the derivative of the inside function. And that simplifies too. Step 2. Find the critical numbers. Critical numbers occur where the derivative equals 0 or is undefined. Let's see where the numerator equals 0. 4x equals 0 when x equals 0. So there's one critical number. Next, let's set the denominator equal to 0. That's when this part equals 0, which is when x is plus or minus 2. So the critical numbers are at x equals minus 2, 0, and 2. Now let's test the intervals. Let's test the value to the left of negative 2. Let's pick negative 3. Find f prime of negative 3. Is it positive or negative? Plugging in negative 3 into our derivative, the numerator is negative and the denominator is positive. So f prime is negative, is less than 0. That means the function is decreasing on that interval. Now let's check the interval between negative 2 and 0. Let's pick negative 1. What's f prime of negative 1? Is it positive or negative? Plugging in minus 1 into our derivative, the numerator is negative and the denominator is negative. So f prime is greater than 0, meaning our function is increasing. So at x equals minus 2, we see that the derivative changes from negative to positive. There's a local minimum at f of minus 2. Let's keep going and check the interval between 0 and 2. Let's pick x equals 1. What's f prime of 1? Is it greater than or less than 0? F prime of 1, the top is positive and the bottom is negative. The derivative is negative, meaning our function is decreasing on that interval. That means at x equals 0, we have a local maximum, because at x equals 0, the derivative changes from positive to negative. Finally, let's check the interval to the right of 2. Let's pick x equals 3. What's f prime of 3? Is the derivative positive or negative? F prime of 3, the top is positive, and the bottom is also positive. In other words, f prime is greater than 0, and our function is increasing on that interval. So that means at x equals 2, we have a local minimum, because the derivative changes from negative to positive. So our final answer, we have a local minimum at the point minus 2, 0, and at 2, 0. And we have a local maximum at 0, cube root 16, since f of 0 is minus 4 to the 2/3, which is equal to cube root 16.